I am the virtual teacher at Egnatia Career College. Today we'll teach Recreation Room, Branch Circuits for Workshop and Utility Area, Heat Detectors, Smoke and Carbon Monoxide Alarms, and Security Systems. This is video number 13. Recreation Room. After studying this unit, you should be able to understand 3-wire, multi-wire circuits, the advantages and the cautions. Understand how to install lay-in fixtures. Calculate what's loss and voltage drop in 2-wire and 3-wire circuits. Understand the term fixture drops. Understand the advantages of installing multi-wire branch circuits. Understand problems that can be encountered on multi-wire branch circuits as a result of open neutrals. Recreation room lighting. The recreation room ceiling is finished with 13 mm gypsum board. 6 lay-in 600 mm by 1200 mm fluorescent fixtures are installed into 600 mm by 1200 mm plaster frames that are fastened to the ceiling's framing. The fixtures rest inside of the plaster frames. A suspended ceiling is another type of ceiling finish often used in recreation rooms. A T-bar ceiling grid is installed below the ceiling joists. Fluorescent fixtures can be installed directly on top of ceiling T-bars. A typical suspended ceiling installation is shown in this figure. This figure shows a device and wiring layout. When conduit is used, junction boxes are mounted above the drop ceiling, usually within half a meter of the intended fixture location. 1 to 2 meters of AC90 armored cable are installed between these junction boxes and the fixtures. These short cables are commonly called fixture drops. They must contain the correct type and size of conductor for the Canadian Electrical Code, CEC, temperature ratings and load requirements for recessed fixtures. In houses wired with non-metallic sheathed cable, the luminaire may be wired directly using NMD90. Fluorescent fixtures of the type shown in this figure might bear the label recessed fluorescent fixture, which might also state suspended ceiling fluorescent fixture. Although they might look the same, there is a difference. Recessed fluorescent fixtures are intended for installation in cavities in ceilings and walls and are to be wired according to Rules 30-900 through 30-912. These fixtures may also be installed in suspended ceilings if they have the necessary mounting hardware. Suspended fluorescent fixtures are intended for installation only in suspended ceilings where the acoustical tiles, lay-in panels, and suspended grid are not part of the actual building structure. The National Building Code and most electrical inspection departments require fixtures to be chained. This provides an independent means of support so, if the ceiling collapses, the fixtures remain supported. Canadian Standards Association (CSA) Standard C22.2E598 covers recessed and suspended ceiling fixtures in detail. How to connect recessed lay-in fixtures. This figure shows how to connect these fixtures. A junction box is located above the ceiling near the fixture. Fixture drops are usually made up of number 14 over 2 AC90 cable if non-combustible construction is used. This cable must be supported a maximum of 300 mm from the box, Rule 12-618. NMD90 cable can also be installed directly into fixtures and looped between fixtures if combustible construction is used. Rule 12-1004A permits 12 mm flexible metal conduit in lengths not to exceed 1.5 meter to make the connection between the junction box and the fixture. Bonding of the fixture is done according to Rule 10-610. When flexible metal conduit is used, a bonding conductor must be run as per Rule 10-610-3. A fixture drop of flexible metal conduit is not required to be supported if the drop is no more than 900 mm, Rule 12-1010-3. However, many electricians secure the flex within 300 mm of the outlet box to avoid pulling the flex out of the connector while they are making up the electrical connections and installing the fixture in the lay-in ceiling. The LED fluorescent fixture style in the main area of the recreation room is 4 lamp fixtures having 3500K cool white lamps installed in them. They are controlled by a single pole switch located at the bottom of the stairs. Circuit B14 feeds the LED fluorescent fixtures in the recreation room. Table 19-1 summarizes the outlets and estimated load for the recreation room. Receptacles and wet bar. The circuitry for the recreation room wall receptacles and the wet bar lighting area introduces a new type of circuit: a multi-wire or 3-wire circuit. Using a multi-wire circuit can save money since one 3-wire circuit will do the job of 2 2-wire circuits. Also, if the loads are nearly balanced in a 3-wire circuit, the neutral conductor carries only the unbalanced current. This results in less voltage drop and watts loss for a 3-wire circuit compared to similar loads connected to 2 separate 2-wire circuits. These figures illustrate the benefits of a multi-wire circuit for watts loss and voltage drop. The example is a purely resistive circuit with equal loads. Example 1 illustrate calculations of voltage available at load. Example 2 illustrates calculations of voltage available at each load. You can pause the video and take your time to understand. The distance from the load to the source is 15 meters. The conductor size is 14 AWG copper. The resistance of each 15-meter length of 14 AWG is about 0.154 ohm. The maximum distance that a 14/2 NMD90 copper wire, based on a 3% voltage drop, may be run is 18.3 meter, using table D3 at a 10 ampere load. Therefore, for runs longer than 20 M in residential applications, table D3 should be used to ensure that the wire is not too small. Rule 8-102 and Appendix D. It is apparent that a multi-wire circuit can greatly reduce watts loss and voltage drop. This is the same reasoning that is used for the 3-wire service entrance conductors and the 3-wire feeder to panel B in this residence. It is important to connect the neutral according to Rule 4-0304, which states that the continuity of the identified, white, conductor must be independent of the device connections. This means that a pigtail connection must be made at receptacles and lamp holders, see Unit 11, Figure 11-5. Take care when connecting a 3-wire circuit to the panel. The black and red conductors must be connected to the opposite phases in the panel to prevent heavy overloading of the neutral, white, conductor. A 2-pole breaker may be used for this purpose, but is not mandatory for multi-wire circuits serving fixed lighting and not split receptacles, Rule 14-010b. The neutral conductor of the 3-wire cable carries the unbalanced current. This current is the difference between the current in the black wire and the current in the red wire. For example, if one load is 12 amperes and the other is 10 amperes, the neutral current is the difference between these loads, 2 amperes. If the black and red conductors of the 3-wire cable are connected to the same phase in panel A, the neutral conductor must carry the total current of both the red and black conductors rather than the unbalanced current. As a result, the neutral conductor will be overloaded. All single-phase, 120/240-volt panels are clearly marked to help prevent an error in phase wiring. The electrician must check all panels for the proper wiring diagrams before beginning an installation. This figure shows how an improperly connected 3-wire circuit results in an overloaded neutral conductor. If an open neutral occurs on a 3-wire circuit, some electrical appliances in operation may experience voltages higher than normal for the circuit. This figure shows that for an open neutral condition, the voltage across load A decreases and the voltage across load B increases. If the load on each circuit changes, the voltage on each circuit also changes. According to Ohm's law, the voltage drop across any device in a series circuit is directly proportional to the resistance of that device. Therefore, if load B has twice the resistance of load A, then load B will be subjected to twice the voltage of load A for an open neutral condition. To ensure the proper connection, take care when splicing the conductors. This figure shows what can occur if the neutral of a 3-wire multi-wire circuit opens. Trace the flow of current from phase A through the television set, then through the toaster, then back to phase B, thus completing the circuit. The following simple calculations show why the television set, or stereo or home computer, can be expected to burn up. With the neutral broken, the TV and the toaster are connected in series across 240 volts. You can see the calculations illustrated in this slide. The toaster that is rated at 1700 watts is producing only 62 watts, whereas the TV that is rated at 180 watts is producing 587 watts. Therefore, the toaster will produce little heat, and the TV components will be damaged, with a possibility of fire. This example illustrates the problems that can arise with an open neutral on a 3-wire, 120 or 240-volt multi-wire branch circuit. The same problem can arise when the neutral of the utility company's incoming service entrance conductors, underground or overhead, opens. The problem is minimized because the neutral of the service is solidly connected, grounded, to the building's water piping system or other approved grounding electrode, Rule 10-102. However, there are cases where poor service grounding has resulted in serious and expensive damage to appliances within the home because of an open neutral in the incoming service entrance conductors. 3-wire circuits are used occasionally in residential installations. The 2 hot conductors of 3-wire cable are connected to opposite phases. 1 white neutral, grounded, conductor is common to both hot conductors. All 3-wire cables supplying multi-wire circuits must be connected to a common trip, 2-pole breaker unless they feed fixed lighting loads or non-split receptacles, Rule 14-010b. The 2 receptacle outlets above the wet bar in the recreation room are ground fault circuit interrupter, GFCI, protected as indicated on the plans. All receptacles within 1.5 meter of a sink require GFCI protection, Rule 26-704. A single pole switch to the right of the wet bar controls the 4 recessed fixtures above it. See Unit 10 for information on recessed fixtures. An exhaust fan similar to the one in the laundry room is installed in the ceiling of the recreation room to exhaust stale, stagnant, and smoky air from the room. The basic switch, receptacle, and fixture connections are similar to those discussed in previous units. The selection of wall boxes for the receptacles is based on the measurements of the furring strips on the walls. 2x2 furring strips will require the use of shallow device boxes. If the walls are furred with 2x4s, regular sectional device boxes could be used. Select a box that can contain the number of conductors, devices, and connectors to meet CEC requirements, as discussed in this text, CEC Table 23. After all, the installation must be safe. Branch circuits for workshop and utility area. After studying this unit, you should be able to understand the meaning, use, and installation of multi-outlet assemblies. List the requirements for a deep well jet pump installation. Calculate, given the rating of the motor, the conductor size, conduit size, overcurrent, and overload protection required for the pump circuit. List the electrical circuits used for connecting electric water heaters. Describe the basic operation of the water heater. Make the proper grounding connections for the water heater. Workshop. The workshop area is supplied by 4 circuits, as you see in this table. A single pole switch at the entry controls all 5 ceiling porcelain lamp holders. However, note on the plans that 2 of these lamp holders have pull chains to allow the homeowner to turn these lamp holders on and off as needed to save energy. In addition to supplying the lighting, circuit S17 feeds the chime transformer and ceiling exhaust fan. The current draw of the chime transformer is extremely small. Table 20-1 shows the estimated load for lighting. Table 20-2 shows the load for the other 3 15-ampere circuits. See also Rules 30-104A and 14-600. Workbench lighting. Two 2-lamp, 17-watt LED fixtures are mounted above the workbench to reduce shadows over the work area. The electrical plans show that these fixtures are controlled by a single pole wall switch. Either a junction box is mounted immediately above or adjacent to the LED fixture so that the connections can be made readily, or the fixture may be directly wired with NMD90. NMD90 can be used to connect the fixture to the junction box. Flexible cord, type S, SJ, or equivalent, cannot be used to connect the fixture to the junction box since it cannot be used as a substitute for the fixed wiring of structures, Rule 12-402-3. The LED fixture must be grounded. Receptacle outlets. Rule 26-720-E stipulates that at least one duplex receptacle shall be provided in any unfinished basement area. Rule 26-720-L requires that at least one duplex receptacle be provided for a central vacuum system where the ductwork is already installed. In this residence, the outlet for the central vacuum is in the garage. In some jurisdictions, the installation of a sump pump in the basement is mandatory. A separate circuit is recommended for the receptacle feeding the sump pump and does not have to be ground fault circuit interrupter (GFCI) protected or AFCI protected. Cable installation in basements. Unit 5 covers the installation of non-metallic sheath cable, Romex, and armored cable, BX. Running non-metallic sheath cable is covered by the 12-500 series of rules, and armored cable, BX, installations by the 12-600 series of rules. When laying out the basement, consider the following. When run through holes in the joists, cables are considered to be supported. Cables for concealed installations must be kept at least 32 mm from the edge of the joist. Check with your local inspection authority to see how many cables may be run through holes in the joists before Rule 4-004-13 is applied. When cables are run near heating ducts, they must be 25 mm from the duct to prevent heat transfer from the duct to the cable. If it is not possible to obtain a 25 mm separation, a thermal barrier must be installed. Running the cable below the ducts whenever possible will also help prevent heat transfer from the ducts. If the cable is run near a concrete or masonry chimney, a distance of 50 mm must be maintained between the conductor and a chimney, and 150 mm must be maintained between the conductor and a chimney cleanout. Some installations will require drilling of the basement joists. To make the cable easier to pull, start at one end of the basement and drill every second joist. At the end of the run, turn around and drill the remaining joists from the opposite direction. The cable will be much easier to pull through holes drilled this way. Multi-outlet assembly. A multi-outlet assembly has been installed above the workbench. For safety and adequate wiring, any workshop receptacles should be connected to a separate circuit. In the event of a malfunction in any power tool commonly used in the home workshop, saw, planer, lathe, or drill, only receptacle circuit A19 is affected. The lighting in the workshop is not affected by a power outage on the receptacle circuit. The installation of multi-outlet assemblies must conform to the requirements of Rule 12-3028. Load considerations for multi-outlet assemblies. A maximum of 12 outlets are permitted on any 2-wire circuit. These outlets have a load of 1 ampere each. The maximum load is, therefore, 12 amperes, which is 80% of the 15 ampere circuit breaker that feeds circuit A19. Where a number of appliances may be used simultaneously, each 300 mm of multi-outlet assembly is considered to be one outlet, Rule 8-304-4. Because the multi-outlet assembly has been provided in the workshop for plugging in portable tools, a separate circuit A19 is provided. This circuit has been included in the service entrance calculations as part of the general lighting and power load requirements for the residence. Many types of convenience receptacles are available for various sizes of multi-outlet assemblies, including duplex, single-circuit grounding, split-circuit grounding, and duplex split-circuit receptacles. Wiring the multi-outlet assembly. The electrician first attaches the base of the multi-outlet assembly to the wall or baseboard. The receptacles are snapped into the base. Covers are then cut to the lengths required to fill the spaces between the receptacles. Manufacturers of these assemblies can supply prefabricated covers to be used when evenly spaced receptacles are installed. These receptacles are usually installed 300 mm or 450 mm apart. In general, multi-outlet installations are simple because of the large number of fittings and accessories available. Connectors, couplings, ground clamps, blank end fittings, elbows for turning corners, and end entrance fittings can all be used to simplify the installation. Empty conduits. Although not truly part of the workshop wiring, Specification 13 and Note 8 on the first floor electrical plans indicates that two empty 27 mm EMT raceways are to be installed, running from the workshop to the attic. This is unusual but certainly handy when additional wiring might be required at some later date. The empty raceways will provide the necessary route from the basement to the attic, thus eliminating the need to fish through the wall partitions. Utility room. In the utility room, the water pump and water heater require special purpose outlets. Water pump circuit. All dwellings need a good water supply. City dwellings generally are connected to the city water system. In rural areas, where there is no public water supply, each dwelling has its own system in the form of a well. The residence plans show that a deep well pump is used to pump water from the well to the various plumbing outlets. The outlet for this pump is shown by the symbol B. An electric motor drives the pump. A circuit must be installed for this system. Jet pump operation. This figure shows the major parts of a typical jet pump. The pump impeller wheel circled as 1 forces water down a drive pipe. Circled as 2 at a high velocity and pressure to a point just above the water level in the well casing. Some well casings may be driven to a depth of more than 30.5 meters before striking water. Just above the water level, the drive pipe curves sharply upward and enters a larger vertical suction pipe circled as 3. The drive pipe terminates in a small nozzle or jet circled as 4. In the suction pipe, the water emerges from the jet with great force and flows upward through the suction pipe. Water rises in the suction pipe, drawn up through the tailpipe. Circled as 5 by the action of the jet. The water rises to the pump inlet and passes through the impeller wheel of the pump. Part of the water is forced down through the drive pipe again. The remaining water passes through a check valve and enters the storage tank circled as 6. The tailpipe is submerged in the well water to a depth of about 3 meters. A foot valve circled as 7 and strainer circled as 8 are provided at the end of the tailpipe. The foot valve prevents water in the pumping equipment from draining back into the well when the pump is not operating. When the pump is operating, the lower part of the storage tank fills with water, and air is trapped in the upper part. As the water rises in the tank, the air is compressed. When the air pressure is 276 kilopascals, kPa, a pressure switch circled as 9 disconnects the pump motor. The pressure switch is adjusted so that as the water is used and the air pressure falls to 138 kilopascals, the pump restarts and fills the tank again. The pump motor. A jet pump for residential use may be driven by a 1 horsepower (HP) motor at 3,400 RPM. A dual voltage motor is used so that it can be connected to 120 or 240 volts. For a 1 horsepower motor, a higher voltage is preferred since the current at this voltage is half that at the lower voltage. It is recommended that a single-phase, capacitor start motor be used for a residential jet pump. Such a motor is designed to produce a high starting torque, which helps overcome the back pressure within the tank and the weight of the water being lifted from the well. This figure is a diagram of the electrical circuit that operates the jet pump motor and pressure switch. This circuit is taken from Panel A, circuits A5 and A7. CEC Table 45 indicates that a 1 horsepower single-phase motor has a rating of 8 amperes at 230 volts. This motor is provided with internal thermal protection. With this information, the conductor size, conduit size, branch circuit overcurrent protection, and overload protection can be determined for the motor. Conductor size, Rule 28-106-1. Rule 28-106-1 requires that conductors supplying motors have an ampacity of not less than 125% of the motor full load current rating. Therefore, the 8 ampere pump motor would require a minimum of a 10 ampere conductor, which would be a minimum number 14 AWG. However, the schedule of special purpose outlets in the specification states that number 12 AWG conductors are to be used for the pump circuit. Conduit size. If rigid PVC conduit is run from the house to the wellhead, 2 number 12 and 1 number 14 AWG T90/TWN75 conductors require 16 mm conduit, Rules 12-910 and 12-1120. Branch circuit overcurrent protection, Rule 28-200, Tables 29 and D16. Rule 28-200 requires the jet pump motor to be protected with an overcurrent device sized according to Table 29. Therefore, Table 29, Line 1, can be used. Motor circuit overcurrent sizing may be determined using Table D16, which is based on Table 29. However, since not all motor full load current ratings are listed in this table, the overcurrent devices should be sized according to Table 29 and Rule 28-200 as you see in this slide. The previously mentioned percentage ratings, as indicated in Table 29 and Rule 28-200-4, are maximum values. If the value calculated by this method does not correspond to a standard size or rating of overcurrent device from Table 13, the next smaller size must be used. However, overcurrent devices smaller than 15 amperes are not required, Rule 28-200-3. Overcurrent devices may be sized smaller than the maximum allowable size if desired. Overload protection for the motor, Rule 28-300. All motors are required to have overload protection, Rule 28-300, unless they meet the requirements of Rule 28-308. Overload devices can be time delay fuses or thermal devices of the fixed or adjustable type. When sizing overload devices, it is important to note the motor service factor, which is indicated on the motor nameplate. If the motor has a marked service factor of 1.15, 115% or greater, the overload devices are sized at 125% of the motor full load current, Rule 28-306-1. If the service factor is less than 1.15, 115%, or is unknown, the overload devices will be sized at a maximum of 115% of the motor FLA. Assuming that the pump has, as most modern motors do, a service factor of 1.15 or greater, the overloads will be sized as 8 amperes times 125% equal 10 amperes. Wiring for the pump motor circuit. The water pump circuit is run from panel A circuits A5 and A7 to a disconnect switch and controller mounted on the wall next to the pump. Thermal overload devices, also called heaters, are installed in the controller to provide overload protection. 2 number 12 conductors are connected to the double pole, 20 ampere branch circuit overcurrent protective device in panel A to form circuit A5/A7. Dual element, time delay fuses may be installed in the disconnect switch. These fuses will serve the dual function of providing both branch circuit overcurrent protection for the pump motor and backup protection for the thermal overload protecting the motor. These fuses may be rated at not more than 125% of the full load running current of the motor. A short length of flexible metal conduit is connected between the load side of the thermal overload switch and the pressure switch on the pump. This pressure switch is usually connected to the motor at the factory. This figure shows a double-pole pressure switch at E. When the contacts of the pressure switch are open, all conductors feeding the motor are disconnected. Submersible pump. This figure shows the major components of a typical submersible pump. A submersible pump consists of a centrifugal pump, circled as 1, driven by an electric motor, circled as 2. The pump and the motor are contained in one housing, circled as 3, submersed below the permanent water level, circled as 4, within the well casing, circled as 5. The pump housing is a cylinder 3 to 5 inch in diameter and 2 to 4 feet long. When running, the pump raises the water upward through the piping, circled as 6, to the water tank, circled as 7. Proper pressure is maintained in the system by a pressure switch, circled as 8. The disconnect switch, circled as 9, high pressure safety cutoff switch, circled as 10, and controller, circled as 11, are installed in logical and convenient locations near the water tank. Some water tanks have a pre-charged air chamber containing a vinyl bag that separates the air from the water. This assures that air is not absorbed by the water. The absorption of air causes a slow reduction of the water pressure, and, ultimately, the tank will fill completely with water with no room for the air. The use of a vinyl bag to hold the air ensures that the initial air charge is always maintained. Power to the motor is supplied by a cable especially designed for use with submersible pumps. Circled as 12, marked submersible pump cable, this cable is generally supplied with the pump and its other components. The cable is cut to the proper length to reach between the pump and its controller. When needed, the cable may be spliced according to the manufacturer's specifications. Rule 26-954 details the wiring permitted for deep well submersible pumps. Submersible water pump cable is tag marked for use within the well casing for wiring deep well water pumps where the cable is not subject to repetitive handling caused by frequent servicing of the pump unit. The wiring from the wellhead to the main distribution panel must be in accordance with CEC Section 12. Should it be required to run the pump circuit underground for any distance, it is necessary to install underground feeder cable type NMWU, or a raceway with suitable conductors, and then make up the necessary splices in an approved weatherproof junction box. This figure illustrates how to provide proper bonding of a submersible water pump and the well casing. Proper grounding of the well casing and the bonding of the submersible pump motor will minimize or eliminate stray voltage problems that could occur if the pump is not bonded to ground. Key Canadian Electrical Code (CC) rules that relate to bonding water pumping equipment are 26-954D. Pumps shall be bonded to ground according to Section 10. 10-600, motors operating at more than 30 volts must be bonded to ground. 10-614, bonding conductor size. 10-708, bond water piping system to ground with number 6 copper. See Unit 24 for information about underground wiring. The controller contains the motor starting relay, overload protection, starting and running capacitors, lightning arrestor, and terminals for making the necessary electrical connections. Thus, there are no moving electrical parts with the pump itself, such as would be found in a typical single-phase, split-phase induction motor that would require a centrifugal starting switch. The calculations for sizing the conductors, and the requirements for the disconnect switch, the motor's branch circuit fuses, and the grounding connections are the same as those for the jet pump motor. The nameplate data and instructions furnished with the pump must be followed. Water heater circuit. Symbol is a triangle with letter C. All homes require a continuous supply of hot water. To meet this need, one or more automatic water heaters are installed close to the areas in the home with the greatest need for hot water. The proper size and type of water piping is installed to carry the heated water from the water heater to the plumbing fixtures and to the appliances that require hot water, such as clothes washers and dishwashers. Modern water heaters have adjustable temperature regulating controls that maintain the water temperature at the desired setting, generally within a range of 45 to 75 degrees Celsius. For safety reasons, the Canadian Standards Association (CSA) requires that electric water heaters be equipped with a high-temperature cutoff. This high-temperature control limits the maximum water temperature to about 96 degrees Celsius. This control is set at the factory and cannot be changed in the field. Electric water heaters shall be equipped with a temperature limiting means in addition to the control thermostat. This temperature limiting means must disconnect all ungrounded conductors. In most residential water heaters, the upper thermostat is set so that it will not exceed 90 degrees Celsius, and the high temperature cutoff is set so that the water temperature does not exceed 96 degrees Celsius. They are usually combined in one device. Most customers will, for safety reasons, ask for a setting less than the maximum. See the section Scalding from hot water later in this unit. The plumber usually installs pressure/temperature relief valves into an opening provided and marked for the purpose on the water heater. The plumber also installs tubing from the pressure/temperature relief valve downward to within 150 mm of the floor so that any discharge will exit close to the floor. This reduces the possibility of scalding someone who might be standing nearby. The water heater manufacturer can also provide a factory-installed pressure-temperature relief valve. Pressure-temperature relief valves are installed to prevent the water heater tank from rupturing under excessive pressures and temperatures, should the adjustable thermostat and the high-temperature cutoff fail to open. This failure would allow the water to boil, 100 degrees Celsius, and create steam, and could lead to the tank rupturing. Residential water heaters typically are available in 60, 101, 170, 225, and 270L sizes. To reduce corrosion, most water heaters have glass-lined steel tanks and contain 1 or 2 magnesium anodes, rods, permanently submerged in the water. Their purpose is to provide cathodic protection. Simply stated, corrosion problems are minimized as long as the magnesium anodes are in an active state. Information about replacing the anode is in the manufacturer's literature included with every electric water heater. Heating elements. The wattage ratings of electric water heaters vary greatly, depending on the size of the heater in liters, the speed of recovery desired, local electric utility regulations, and local plumbing and building codes. Wattage ratings are usually 1,650, 2,000, 2,500, 3,000, 3,800, 4,500, or 5,500 watts. Other wattage ratings are available. The heating elements are generally rated 240 volts. Elements are also available with 120 volt ratings and 208 volt ratings. These elements will produce rated wattage output at rated voltage. When operated at less than rated voltage, the wattage output will be reduced. The effective voltage variation is discussed later in this unit. Most heating elements will burn out if operated at voltages 5% higher than that for which they are rated. To reduce the element burnout situation, some manufacturers will supply water heaters with heating elements that are actually rated for 250 volts, but will mark the water heater 240 volts with its corresponding wattage at 240 volts. This allows a cushion should higher than normal voltages be experienced. CSA Standard CAN/CSAC 22.20. 110M90, entitled Construction and Test of Electric Storage Tank Water Heaters, details the specifications and test procedures for water heater storage tanks and elements. Heating elements consist of a high-resistance nickel, chrome, nichrome, alloy wire that is coiled and embedded, compacted, in magnesium oxide in a copper-clad, or stainless steel, tubular housing. The magnesium oxide is an excellent insulator of electricity, yet it effectively conducts the heat from the nichrome wire to the housing. The construction of heating elements is the same as that of the surface units of an electric range. Terminals are provided on the heating element for the connection of the conductors. A threaded hub allows the element to be screwed securely into the side of the water tank. Water heater resistance heating elements are in direct contact with the water for efficient transfer of heat from the element to the water. Electric water heaters are available with 1 or 2 heating elements. Single-element water heaters have the heating element located near the bottom of the tank. 2-element water heaters have one heating element near the bottom of the tank and the other about halfway up. Thermostats, as illustrated in this figure, turn the heating elements on and off, thereby maintaining the desired water temperature. In 2-element water heaters, the top thermostat is an interlocking type, sometimes referred to as a snap-over type. The bottom thermostat is a single pole, on-off type. Both thermostats have silver contacts and have quick make-and-break characteristics to prevent arcing. The various wiring diagrams in this unit mention that both heating elements cannot be energized at the same time. Speed of recovery. Speed of recovery is the time required to bring the water temperature to satisfactory levels in a given time. The current accepted industry standard is based on a 32.22 degrees Celsius rise. For example, Table 20-3 shows that a 3,500 watt element can raise the water temperature 90 degrees Fahrenheit 32.22 degrees Celsius of a little more than 16 gallons, about 60 liters, an hour. A 5,500 watt element can raise water temperature 90 degrees Fahrenheit 50 degrees Celsius of about 25 gallons, about 95 liters, an hour. Speed of recovery is affected by the type and amount of insulation surrounding the tank, the supply voltage, and the temperature of the incoming cold water. The eventual temperature should be 57.22 degrees Celsius for health reasons. Scalding from hot water. The following are plumbing code issues but are discussed briefly because of their seriousness. Temperature settings for water heaters pose a dilemma. Set the water heater thermostat high enough to kill bacteria on the dishes in the dishwasher and possibly get scalded in the shower. Or set the thermostat to a lower setting and not get scalded in the shower, but live with the possibility that bacteria will still be present on washed dishes. In the United States, the Consumer Product Safety Commission reports that 3,800 injuries and 34 deaths occur each year due to scalding from excessively hot tap water. Unfortunately, the victims are mainly the elderly and children under the age of 5. They recommend that the setting should not be higher than 49 degrees Celsius. Some state laws require that the thermostat be preset at no higher than 49 degrees Celsius. Residential water heaters are all preset by the manufacturer at degree 49 grade Celsius. Manufacturers post caution labels on their water heaters that read something like this. Scald hazard. Water temperature over 49 degrees Celsius can cause severe burns instantly or death from scalds. See instruction manual before changing temperature settings. To reduce the possibility of scalding, today's single-handle shower and sink taps have a thermostatic non-scald mixing valve or pressure balancing valve that holds a selected water temperature to within 1 degree, regardless of incoming water pressure changes. This prevents sudden unanticipated changes in water temperatures. Table 20-4 shows time/temperature relationships relating to scalding. What about washing dishes? Older automatic dishwashers required incoming water temperature of 60 degrees Celsius or greater to get the dishes clean. A water temperature of 49 degrees Celsius is not hot enough to dissolve grease, activate powder detergents, and kill bacteria. That is why commercial and restaurant dishwashers boost temperatures to as high as 82 degrees Celsius. Newer residential dishwashers have their own built-in water heaters to boost the incoming water temperature in the dishwasher from 49 degrees Celsius to 60 degrees Celsius to 63 degrees Celsius. This heating element also provides the heat for the drying cycle. Today, a thermostat setting of 49 degrees Celsius on the water heater should be satisfactory. Sequence of operation. Water heaters can be connected in many ways, usually depending on the local power company's regulations. This book illustrates only 3 types of connections. Consult your power utility and/or your supplier of electric water heaters to find out what connections are available in your area. This figure shows the wiring for flat-rate connection, where electricity to the water heater is off during peak load periods of the day. This is controlled by the hydro utility. Generally, the flat rate charge depends on the size of the hot water tank in the residence. This figure shows the wiring for connection to the main panel, so that the kilowatt-hour power consumption of the water heater is metered, but has the advantage of having 24-hour operation. When all of the water in the tank is cold, the upper element heats only the water in the upper half of the tank. The upper element is energized through the lower contacts of the upper thermostat. The lower thermostat also indicates that heat is needed, but heat cannot be supplied because of the open condition of the upper contacts of the upper thermostat. When the water in the upper half of the tank reaches a temperature of about 49 degrees Celsius, the upper thermostat snaps over, the upper contacts are closed and the lower contacts of the upper thermostat are opened. The lower element now begins to heat the cold water in the bottom of the tank. When the entire tank is heated to 49 degrees Celsius, the lower thermostat shuts off. Electrical energy is not being used by either element at this point. The heat insulating jacket around the water heater is designed to keep the heat loss to a minimum. Thus, it takes many hours for the water to cool only a few degrees. Most of the time, the bottom heating element will keep the water at the desired temperature. If a large amount of hot water is used, the top element comes on, resulting in fast recovery of the water in the upper portion of the tank, which is where the hot water is drawn from. Metering and sequence of operation. Electric water heaters are available in a number of styles. Single element. Double element, simultaneous operation. Double element, non-simultaneous operation. There are several ways that a utility company can provide metering and for the electrician to make the connections. 1. Connect the water heating to one of the two-pole, 240-volt circuits in the main distribution panel. This is probably the most common method because the wiring is simple and additional switches, breakers, time clocks, or meters are not required. This is the connection for the residents used as an example in this textbook. This method provides electricity to the water heater 24 hours of every day. 2. Connect the water heater in a flat rate arrangement. The utility supplies power to the consumer via a 4-wire cable. This contains the 3 feeder lines and a 4th wire to control the water heater during peak demand periods. This wire is connected to a separate terminal block located at the 3 o'clock or 9 o'clock position in the meter base. The electrician then connects 2 red numbered 10 AWG solid wires to the terminal block at the 3 o'clock position and to the water heater lug on the line side of the meter base. These wires pass through the service conduit and through the main disconnect into a separate 30-ampere, fusible disconnect. The number 10 has AC90 or NMD90 then connects to the water heater. 3. Connect the water heater circuit, as shown in this figure, but install a time clock in the circuit leading to the water heater. The time clock would be set to be off during certain times of the day deemed peak hours by the utility. The utility gives special incentives to the homeowner for agreeing to this arrangement. This is a good conservation method that many supply authorities are promoting. 4. Some utilities use radio-controlled switching to control water heater loads. They send a carrier signal through the power line, which is received by the electronic controlling device, thereby turning the power to the water heater on and off as required by the utility. This is commonly called a flat-rate water heater. The utility will charge a fixed rate regardless of the energy used. This is still very common in many centers. Water heater load demand. The following CEC rules apply to load demands placed on an electric water heater branch circuit. Rule 8-104(2) requires that a branch circuit shall have a rating not less than the calculated load of the heater. Rule 8-104(6)(a) requires that a continuously loaded appliance must have a branch circuit rating not less than 125% of the marked rating of the appliance. Disconnecting means. Rule 26-746 requires that the appliance have a means of disconnect. This would normally be located in the panel, load center, or it could be provided by a separate disconnect switch. Rule 14-416 allows the unit to have a switch that is an integral part of the appliance having an off position and capable of disconnecting all ungrounded conductors from the source, to be considered the required disconnecting means. In many local codes, however, this is not acceptable. Rules 14-300 and 14-408 require that switches and circuit breakers used as the disconnecting means be of the indicating type, meaning they must clearly show that they are in the on or off position. Branch circuit overcurrent protection. The rating or setting of overcurrent devices shall not exceed the allowable ampacity of the conductors they protect, Rule 14-104. Therefore, the CEC permits the use of a minimum 25 ampere fuse or circuit breaker, Table 13. If the calculated ampacity of an overcurrent device is not a standard value, the next larger standard size must be used. Here, in this example, you can see the calculations. Rule 8-104(2) states that the branch circuit rating shall have an ampacity not less than the maximum load to be served. Rule 8-104(1) states that the branch circuit rating is the lesser of the wire ampacity or that of the overcurrent device. The water heater for the residence is connected to circuit A6A8, a 20 ampere, double-pole overcurrent device located in the main panel in the workshop. This circuit is straight 240 volts and does not require a neutral conductor. Checking Table A-1, Schedule of Special Purpose Outlets, in Appendix A at the back of this textbook, we find that the electric water heater has two heating elements, a 2000 watt element and a 3000 watt element. Because of the thermostatic devices on the water heater, both elements cannot be energized at the same time. Therefore, the maximum load demand is amperes equals watts divided by volts. 3000 watts divided by 240 volts equal 12.5 amperes. For water heaters with two heating elements connected for non-simultaneous, limited demand operation, the nameplate on the water heater will be marked with the largest element's wattage at rated voltage. For water heaters with two heating elements connected for simultaneous operation, the nameplate on the water heater will be marked with the total wattage of both elements at rated voltage. Conductor size. CEC Table 2 indicates that the conductors will be numbered 12 AWG. The specifications for the residence call for conductors to be NMD 90. See specifications 7 and 11. Bonding. If flexible conduit is run from a junction box to the water heater is bonded through a separate bonding conductor sized according to Table 16, which is run in the flex to the box. The heating elements in the water heater in this residence are rated 240 volts. They will operate at a lower voltage with a reduction in wattage. If connected to voltages above their rating, they will have a very short life. In this slide, you can see the calculations. In resistive circuits, current is directly proportional to voltage and can be simply calculated using a ratio and proportion formula. For example, if a 240-volt heating element draws 12.7 amperes at rated voltage, the current draw can be determined at any other applied voltage, say 208 volts. Calculations can be seen here. Also, in a resistive circuit, wattage varies as the square of the current. Therefore, when the voltage on a heating element is doubled, the current also doubles and the wattage increases 4 times. When the voltage is reduced to 1/2, the current is halved, and the wattage is reduced to 1/4. According to these formulas, a 240-volt heating element connected to 208 volts will have about 3/4 of the wattage rating it has at the rated voltage. Heat detectors, smoke and carbon monoxide alarms, and security systems. After studying this unit, you should be able to name the 2 basic types of smoke alarms. Identify the Underwriters Laboratories of Canada, ULC, standard that refers to household fire warning equipment. Discuss the location requirements for the installation of heat detectors and smoke alarms. List the locations where heat detectors and smoke alarms may not be installed. Describe the wiring requirements for the installation of heat detectors and smoke alarms. List the major components of a typical residential security system. Identify the CEC Rule 32 requirements for the installation of residential fire alarm systems. Identify the requirement for the installation of carbon monoxide alarms. The importance of heat detectors and smoke alarms. In recent years, the standards of the ULC, combined with the National Building Code of Canada and associated provincial and municipal codes, have made mandatory the installation of smoke alarms and/or heat detectors in critical areas of a home. A sufficient number of detectors must be installed to provide full coverage. Fire sensing devices commonly used in a residence are heat detectors and smoke alarms. These must be connected to a central fire alarm control panel that will process the information and send an output signal to alarm bells or buzzers. Types of smoke alarms. Photoelectric smoke alarm. In the photoelectric type of smoke detector, a light sensor measures the amount of light in a smoke chamber inside the unit. When smoke is present, an alarm sounds, indicating that light is being reflected off the smoke in the chamber. This type of sensor detects smoke from burning materials that produce great quantities of white or gray smoke, such as furniture, mattresses, and rags. It is less effective for gasoline and alcohol fires, which do not produce heavy smoke. It is also not as effective with black smoke, which absorbs light rather than reflecting it, as gray or white smoke does. Ionization smoke alarms. The ionization type of smoke detector contains a low-level radioactive source that supplies particles that ionize the air in the smoke chamber of the detector. Plates in this chamber are oppositely charged. Because the air is ionized, an extremely small amount of current, millionths of an ampere, flows between the plates. Smoke entering the chamber impedes the movement of the ions, reducing the current flow, which causes an alarm to go off. This type of detector is able to sense products of combustion in the earliest stages of a fire. It can detect airborne particles, aerosols, as small as 5 microns in diameter. The ionization type of detector is effective for detecting small amounts of smoke, as in gasoline and alcohol fires, which are fast flaming. It is also more effective for detecting dark or black smoke than the photoelectric type of detector. Installation requirements. It is mandatory to install smoke alarms and alarms in all new homes. National Building Code of Canada 3.2.4.21.1/9.10.18.1. Do install smoke alarms on each floor of a residence for minimum protection. Make sure that one of these alarms is located between the sleeping area and the rest of the house. These alarms must be interconnected so that if one alarm detects smoke, they all sound. Do install smoke alarms in all rooms, hallways, attics, basements, and storage areas of a residence to provide protection that exceeds the minimum recommendation above. Do install the detector on the ceiling as close as possible to the center of the room or hallway. Do install a smoke alarm on a basement ceiling close to the stairway to the first floor. Do place a detector within 900 mm of the peak on a sloped ceiling that has greater than 300 mm rise per 2,400 mm horizontally. Do install smoke alarms and heat detectors at the top of an open stairway, because heat and smoke travel up. Do install hardwired detectors in new construction. These detectors are directly connected to a 120-volt alternating current (AC) source. For existing homes, either battery-powered units or hardwired 120-volt AC units may be used. Do not install detectors in the dead air space at the top of a stairway that can be closed off by a door. Do not place the edge of a detector mounted on the ceiling closer than 150 mm from the wall. Do not place a wall-mounted detector closer than 150 mm from the ceiling and not farther than 300 mm from the ceiling. The area where the ceiling meets the wall is considered dead air space where smoke and heat may not reach the detector. Do not connect detectors to wiring that is controlled by a wall switch. Do not connect detectors to a circuit that is protected by a ground fault circuit interrupter, GFCI, or an arc fault circuit interrupter, AFCI, Rule 32-200A. Do not install detectors where relative humidity exceeds 85%, for example, adjacent to showers, laundry areas, or other areas where large amounts of visible water vapor exist. Do not install detectors in front of air ducts, air conditioners, or any high draft areas where the moving air will keep the smoke or heat from entering the detector. Do not install detectors in kitchens where the accumulation of household smoke can result in false alarms with certain types of detectors. The photoelectric type may be installed in kitchens, but must not be installed directly over the range or cooking appliance. Do not install where the temperature can fall below 0 degrees Celsius or rise above 50 degrees Celsius. Do not install in garages, vehicle exhaust can set off the detector. Do not install detectors in airstreams that will pass air originating at the kitchen cooking appliances across the detector. False alarms will result. Manufacturer's requirements. Manufacturers of smoke alarms and heat detectors have certain responsibilities. The power supply must be capable of operating the signal for at least 4 minutes continuously. Battery-powered units must be capable of a low battery warning beep of at least 1 beep per minute for 7 consecutive days. Direct-connected 120-volt AC detectors must have a visible indicator that shows power on. Detectors must not signal when a power loss occurs or when power is restored. Features of smoke alarms and heat detectors. Smoke alarms may contain an indicating light to show that the unit is functioning properly. They may also have a test button to test the circuitry and alarm capability. When the button is pushed, it is the circuitry and alarm that are tested, not the smoke detecting ability. Heat detectors are available that sense a specific fixed temperature, such as 57 degrees Celsius or 90 degrees Celsius. Available also are rate of rise heat detectors that sense rapid changes in temperature, 6 degrees Celsius per minute, such as those caused by flash fires. Fixed and rate of rise temperature detectors are available as a combination unit. Combination smoke, fixed, and rate of rise temperature detectors are also available in one unit. The spacing of heat detectors shall be as recommended by the manufacturer, because detectors are capable of sensing heat only within a limited space in a given time. Wiring requirements. Direct connected units. All new construction requires smoke alarms to be connected to a 120-volt circuit that feeds a lighting circuit, Rule 32-200A. Smoke alarms must never be connected to a dedicated circuit. This type of smoke alarm will usually be of the interconnected type and may include other features such as battery backup or a built-in carbon monoxide detector. A direct connect unit with battery backup is shown in this figure. When using interconnected smoke alarms, it is important to refer to the manufacturer's literature for the maximum number of devices allowed. Each manufacturer and model may allow different maximum numbers. When devices are interconnected, all alarms will sound at the same time, regardless of which device actually detected smoke. All new residential construction requires an interconnected smoke alarm on each level of the home and near the bedrooms. If bedrooms are located at opposite ends of a home, it may be necessary to install more than one alarm on a level. Interconnected smoke alarms have one white wire, one black wire, and one red or yellow wire, which is used to interconnect them. Refer to for wiring these devices. Interconnection of these units can also be wireless. Battery-operated units. These units require no wiring, they are simply mounted in the desired locations. Batteries last for about a year. Battery-operated units should be tested periodically, as recommended by the manufacturer. Always follow the installation requirements and recommendations of the unit manufacturer. Refer to the ULC standards for additional technical data relating to the installation of smoke and heat detectors. Combination direct/carbon monoxide alarms battery/feed-through alarms. Combination units are connected directly to a 120-volt AC circuit, not GFCI or AFCI protected, and are equipped with a 9-volt direct current DC battery. In a power outage, these alarms will continue to operate on the 9-volt DC battery. The ability to interconnect a number of alarms offers whole house protection, because when one unit senses smoke, it triggers all of the other interconnected units into alarm mode as well. Because of the vital importance of smoke and fire alarms to prevent loss of life. You should very carefully read the application and installation manuals that are prepared by the manufacturer of the smoke alarms and heat detectors. The residence featured in this textbook has 4 smoke alarms, hardwired directly to a 120-volt AC branch circuit, S16. They are interconnected feed-through units that will set off signaling in all units, should one unit trigger. These interconnected smoke alarms are also powered by a 9-volt DC battery that allows the unit to operate in the event of a failure in the 120-volt AC power supply. Carbon monoxide alarms. National, provincial, and local building codes set the standards for the installation of carbon monoxide (CO) alarms in dwelling units. These may be freestanding units, permanently wired to a source of supply, or part of a smoke detector. If the building code requires hardwired CO alarm, a battery-operated or plug-in device is not acceptable. It must be permanently wired. A CO alarm is required when the dwelling has a solid fuel burning appliance such as a wood stove, wood-burning fireplace, or wood or corn furnaces. The dwelling contains a fuel-burning appliance such as a furnace or fireplace operating from a non-solid fuel such as natural gas, propane, or oil. The dwelling shares a wall with a garage. Location and connection of carbon monoxide alarms. If a solid fuel appliance is used, an alarm must be located on or near the ceiling in the room or area where the appliance is located. When the dwelling uses another source of fuel or shares a wall with a garage, an alarm must be located in each bedroom or outside each bedroom within 5 meters of the bedroom doors, this distance being measured along the corridor. If the house is large and bedrooms are located on multiple floors or at opposite ends of the building, it may require multiple CO alarms. If the dwelling has a solid fuel burning appliance, an alarm in the room with the appliance and detectors near the bedrooms are required. CO alarms may be connected to most 15-ampere lighting and receptacle branch circuits except those used to feed kitchen counter, refrigerator, or dining area receptacles or outlets in garages or located outdoors. They must not be connected to GFCI or AFCI protected circuits or circuits that supply only receptacles. A switching or disconnecting means between the device and the circuit breaker is not allowed. Security systems. It is beyond the scope of this text to cover every type of residential security system. We focus on some of the features available from the manufacturers of these systems. Installed security systems range from simple to very complex. Features and options include intruder detectors for doors and windows, motion detectors, infrared detectors, and under-the-carpet floor mat detectors for space protection. Indoor and outdoor horns, bells, electronic buzzers, and strobe lights can provide audio as well as visual alarm. Telephone interconnection to pre-selected telephone numbers, such as the police or fire departments, is also available. The homeowner and electrician should discuss specific features and benefits of security systems. Most electricians are familiar with a particular manufacturer's selection of systems. This figure shows the range of devices available for such a system. These systems are generally on display at lighting fixture stores that offer the homeowner an opportunity to see a security system in action. Wiring for a security system consists of small, easy-to-install, extra-low voltage, multi-conductor cables made up of number 18 AWG conductors. The actual installation of these conductors should be done after the regular house wiring is completed to prevent damage to these smaller cables. Usually the wiring can be done at the same time as the door chime wiring is being installed. Security system wiring comes under the scope of Section 16. When such detectors as door entry, glass break, floor mat, and window foil are used, circuits are electrically connected in series so that if any part of the circuit is opened, the security system will detect the open circuit. These circuits are generally referred to as closed or closed loop. Alarms, horns, and other signaling devices are connected in parallel, since they will all signal at the same time when the security system is set off. Heat detectors and smoke alarms are generally connected in parallel because all of these devices will close the circuit to the security master control unit, setting off the alarms. Fire detectors are available for series connection for use in security systems that require normally closed contacts for circuit operation. The instructions furnished with all security systems cover the installation requirements in detail, alerting the installer to Canadian Electrical Code (CEC) regulations, clearances, suggested locations, and mounting heights of the system's components. Always check with the local electrical inspection authority to determine if there are any special requirements in your locality for the installation of security systems.